Okay, let's move to the next phenomena called the ferromagnetism. So the ferromagnetism is the phenomena that come from ferromagnetic materials, and inside the ferromagnetic materials, each atom has a competitively large dipole moment that case from primarily by uncompensated electron spins. So I need to explain what is called the uncompensated electron spins. Oops. Okay, typically for the quantum mechanics, we know that the electrons will fill the orbital of the for example, this is a kind of we can say, for example, if this is a chromium 3 plus, for the chromium 3 plus, its electron configuration would be 3D this would be AR, that would be AR 3D3. This is the electron configuration of the trivariant chromium, right? Typically for the pure chrome, it has its electron configuration would be look like the AR 3D5 4S1 due to its incomplete half field share. Okay, so in that case, we will fill the electron like this way. So if this is the 4s orbital, this is the 3d orbital, which is T2g, and this is EG orbital. We will first fill one electron at the 4s orbital, and there are 5 electrons here. Okay, due to the Hang's rule, we will fill parallelly in the orbital first. But for the chromium, trivariant chromium, we will remove 3 electrons. So which 3 would be removed? It would be 1 from the 4x electron and 2 for the 3d electrons. Okay, so this is the reality for the trivariant chromium here. Okay, so in this case, maybe you will have a question, why not fill like this way? Because the Hang's rule tell you that we must fill all the orbital, then we will fill the anti-parallelly. So this is violate to the Hang's rule. Okay, so in this case, the magnetic the spins are all parallel. Then they will give you the total spin angular momentum is equal to the 3/2. Okay, or actually we can write speed 3/2 h bar. Any questions? And who have questions? Hong Chen-Zi, do you have any questions? Hong Shen-Zi, do you have any question? No? Okay. So here we have a 3/2 h bar spin moment. So in this case, we will get the mu is equal to 2 h bar and the 3/2 h bar mu b. So in this case, we will get 3 mu b for chromium trivalent ion. Okay, so this 3 mu b is coming from the uncompensated electron spins. So that's the meaning of uncompensated. Okay, so let's back to this topic. So for the ferromagnetic materials, this computatively large dipole moment caused primarily by these uncompensated electron spins. So each atom carries magnetic moments, and interatoms they have force attract to each other and produce the parallel alignment of the spin over a region that contains large number of atoms. So in these regions we have parallel spins, and so does this one and this one. And in this case, we call if these atoms have identical spin alignment, then we will call this the spin at this area is formed as a magnetic domain, or in brief called domains. And the domains have a variety shape and the size depend on the material sample and its magnetic history. So the magnetic history we will mention about later, which is called historicism. And shown here is the picture for the neodymium ion boron magnet. They have many domains, and this is the picture that's scanned by the magnetic force microscope. So if they have the same color, which means this in this area they have parallel spins. So there are many domains inside the compound. Okay. So in the beginning, these domain moments are generally randomly oriented. So the materials as a whole has no magnetic moment. That's such like if you ever play the magnet that look like a dark or black pellet. And this kind of magnet is made by the ferrites. And if you heat up this magnet to higher temperature, then it will lose its magnetic field. This is because their magnetic domains becomes total randomly, so they will appear no magnetic moment. But upon apply an external field, however, those domains with moments in the direction of the applied magnetic field will increase their size. So they will also affect their neighborhood, and they will create their own internal field. So it will look like this. This is the in the beginning that there are multiple magnetic domains. But when we apply external field, and for example, this one will tend to parallel to this one. So if this one is parallel to this one, then you will see that the magnetic domain size is increased. Okay. As the result, you will find in the final all the spins are parallel to single direction, and then they will create a large magnetic field inside and outside. So this phenomenon is called the ferromagnetism. This is an image of the movement of magnetic domain. So there are black and white color, and each color corresponding to one spin orientation. So when we apply magnetic field, the break one, I think the break one is parallel to the magnetic field. So the break one will increase their size, and finally they will create a single domain. Okay, so one of the special characteristic to the ferromagnetic behavior is historicism, because when we apply external magnetic field, and for example, you can check this picture. This is the initial magnetized curve. So when we increase, the x-axis is the external applying magnetic field, and the y-axis is the magnetization, which is the sum of magnetic dipole moment. Okay, so when we increase the external magnetic field, then the magnetic moment, then the magnetization will also increase with the field. But when we reach a certain value, that means all the spins are parallel. The sum of the magnetic dipole moment, which means the magnetization will not increase anymore, even you further increase the external magnetic field. So this point we call the MS. S means saturation magnetization. And then when we try to remove the external field, which means we will gradually decrease the magnetic field, the magnetization will not decrease again as the initial one, and it will remain have a certain value until the magnetic field equal to 0. So at this point, we call this point is the resonance, which means the reduce the magnetization here, and it will not longer become 0. But when we further decrease, or we apply the anti-parallel, the opposite direction of the magnetic field, the magnetization will further decrease. When we reach the point that have 0 magnetization, this point is called coercivity. So this value represents that the price that you need to eliminate all the magnetic moment to random orientation. So you can imagine that the area here represents the total magnetic energy that is stored in the material. Okay, so this is also a very important parameter that to estimate for those permanent magnet, the performance of those permanent magnet. Okay, so if you repeat this experiment again and again, you will get a hysteresis loop like this. Okay, the large area in this picture, the large magnetic energy stored in the material. Okay, so this effect is called hysteresis, and this loop is called hysteresis loop. For the typical materials such as paramagnetism or diamagnetism, there will be for the paramagnetism there will be a linear, or you will they will give you a line here. If the material is diamagnetism, you will see the line look like this. They will have negative slope because they obey a length law. But for the ferromagnetism, you will see the loop here. So you can judge the material carries which kind of magnetic property by using measuring hysteresis loop. Okay. So the only element that are ferromagnetism at room temperature are iron, nickel, and cobalt. So at a sufficient high temperature, ferromagnet will become a paramagnetic. So we know that they have interatom force here, so they will tend to ally to each other. But if this force is weaker than the thermal energy, the thermal fluctuation will broken the interaction between the atoms, and that loss orientation of magnetic moment to random. So they will not hold alignment again, and their magnetization will become 0 again due to the thermal effect. So in other words, the ferromagnetism and the paramagnetism are actually have same origins, but that appears at different states due to the temperatures. So we can say that the ferromagnetism is the low temperature state of these paramagnetic materials. But this claim is a little bit dangerous, because not all of the materials that have uncompensated magnetic moments. So that would be correct for those materials that they have uncompensated spins. Okay, any questions? No? Okay. So there is another special case for the ferromagnetism, and this case is called antiferromagnetism. So what is antiferromagnetism? That means the magnetic moment of the atom or molecules usually related to the spin of the electrons that align in a regular pattern with neighbor whose spins point in opposite directions. So shown here is the picture of the ferromagnetism. So the spins to their neighborhood is anti-para, no matter along the x direction or y direction. And there is another case called ferrimagnetism. So you can just the prefix of this word is a little bit different. So we have antiferro. Ferro means the para, and the anti means anti-para. But the ferri means the material is the one have a population of atoms with opposing magnetic moments. So in principle, they are antiferromagnetism. But in ferromagnetic materials, the opposite moments are unequal as the spontaneous magnetization remains. So that means although they are anti-para, but the size of the magnetic moment are different. So in the final, we will find they have a residue magnetic moment that looks like, if you look like these two in one unit, the final result is you will see in this unit we have spins toward up, and this one is also toward up. So finally you will find the residue magnetizations and point to the direction up. So in this case, this material will behave like antiferromagnetism, but the final result will look like ferromagnetism. So we give them a different specified word called ferri. So this is ferrimagnetic. So shown here is a temperature profile of 4 kinds of magnetism. And here is a parameter called the chi. So what is the chi mean? We know that the magnetization is the sum of the magnetic moments, and the chi is defined of the m by the b or the h, which is the response of magnetization in the applied magnetic field. Okay, so this is the definition of the chi. We call magnetic susceptibility. Magnetic susceptibility. Okay, so the magnetic susceptibility is equal to C by T by Tc. This is called the Curie-Weiss law. So if we inverse this equation, that means if we inverse the chi, this is 1 over chi, and in this case, C is a constant. So in this case, this is 1 over C by 1 over C times T. And here is the Tc by C. And in this case, because this is the parameter, this is a parameter of temperature, and this is the y-x. So this equation look like y is equal to ax plus b. That should be a linear equation, right? So if you inverse this equation like this form, you will find the behavior of the chi to t will like a linear behavior. So for the paramagnetism, for the paramagnetic materials, the 1 over chi 2t part will look like a straight line. For the ferromagnetic materials, you will find there is a straight line with some intercept at the x, and this point we call it Tc, which is the Curie temperature or critical temperature. And below this point, the magnetic moment tend to align, so they will increase and reach to a certain point, because if the all the magnetic moments are totally aligned, then the chi value will equal to a certain fixed value, so they will reach to 1 point. And for the ferromagnetism, because the coupling stress between the longer magnetic moment or shorter magnetic moment, even between the longer and shorter magnetic moment, are different. So the reciprocal chi will plot like this. It will be curved here due to the different interaction between any two spins. So they will not linearly, they will become a curved, but they will also reach to 1 point, also called the Tc. So the Tc is here and not here. And then from this point, they will also grow up due to they will have strong interaction that they will overcome the thermal fluctuation. So the 1 over chi will raise again and reach to a certain point here, and it will look like the ferromagnetism, right? And for the antiferromagnetism, they will also straight line here because they are above the Tn. Tn is a near temperature, which is also the ordinary temperature of this material. So a linear chain here and becomes a curve here. For the theories, when we reach the t equals 0, this point would be at the infinity, because if we plot these equations, here would be reached if the chi is equal to 0, and then this point will come to the infinity. But in the practical case, that will be also reached to a certain point at very high point on the y-axis. Okay, so this is the sketch for the antiferromagnetism. So 4 kinds of magnetism are plotted here, and the most important phenomena that we can observe is the paramagnetism, because all these four cases will appear a straight line when they above the ordering temperature, no matter it's called the Curie temperature, critical temperature, or near temperature. Okay, any questions? No. So I think you need to familiar in these four magnetism, because when we talk the application of this emergent magnetic material, you need to know which kind of material you should use. Maybe for the biochemistry, you may choose the paramagnetism for those thermal therapies. Maybe you can choose the ferromagnetic one or paramagnetic one, depends on which kind of energy that you need to absorb. And maybe in some case you will adjust in between the paramagnetism or ferromagnetism. You need to choose the ferromagnetic material that will give you a proper energy absorption. So you must have some basic idea about the origin of this magnetic behavior, or the catalog of the magnetic ordering. Okay. No any questions? Okay, so I will give you a more detail of this magnetic ordering. So there will be some mathematics, but maybe you can you can know how does this come, but you don't need to know very detail about this mathematical equations. But I will still derive the how did they come to you, and then have some idea. Maybe for the students come from the physical chemistry department, you can improve the performance of the material. For the bioscience department students, maybe you can just understand and can communicate with those material engineers how to which kind of the material that you want apply to the bio to the bio sorry to the bioinactive to looking for the bioinactive material. Okay, so the first one is the diamagnetism, and the diamagnetism is coming from the Lenz's law. I already know Lenz's law in the atomic scale, and we will give you the diamagnetism from the classical point of view. And I also need to mention again, this picture is totally wrong in quantum mechanics, but it's still valuable to understand the detail of the origin of the diamagnetism. Okay, so supposedly we have applied external magnetic field and slowly increased it in the vicinity of an atom. Then as the magnetic field change, and so we know the magnetic field will change the electric field in the generality by magnetic induction. So this is typically Faraday's law. Maybe you already learned in the general physics book. So from the Faraday's law, the line integral of the E along the cross path, that means there would be create the electric field that along this cross loop. okay, is the rate of the change of magnetic flux through the path. So this path encloses an area here, and the magnetic flux will correlate with the electron field increase along this line path. Okay, so they have a relation. The magnetic field here and the electric field here, they have some relations, and that would be Faraday's law. Okay, suppose we pick a path gamma, which is a circle of the radius r, concentric with the center of the atom. Then the average tangential electric field around this path is given by E times 2 pi is equal to minus d of dt b pi r square. Okay, this is the Faraday's law or induction law. So that means if we change the magnetic flux inside this loop, they will create an electric field along this path. So in this case, we will write the E is equal to minus r by 2 dB dt. So this is the time ratio of the time change ratio of the applied magnetic field. Okay. Then, so the induced electric field act on an electron is an atom produce a torque equal to the minus QER, which must equal to the rate of change of the angular momentum. So let me show you here. So this is Faraday's law here, and we can make a conclude that E is equal to minus 2R dB dt. And we also know the torque is equal to the dl dt. L is angular momentum, right? And this would be right as there will be a little something wrong. Wait a moment. Oh, okay, sorry. That should be right like this. Okay. So the time rate of the torque change will be right like this. So the tau, the t tau is the torque that the electron experience. So the torque, the t would be right as r cross f, and r is the radius of the electron that's orbit this. This is the r, and this is the f, and we have the torque is equal to r cross f. Okay. And this torque would be changed by the external magnetic field. So we can write the tau dt is equal to the tau of dt r cross f, and the r is the radius here, and the force is coming from the static electron force. So that would be equal to QE. So the F is equal to QE. Okay. And the of the RQE here, you may put the E here, and the R and the Q is not the variable of the time, so we can write the equation look like minus 2QR dB dt. Okay, so we know that the delta mu is equal to minus 2mq by delta L. So this is the ratio between the charge and the mass. and this time change is equal to the tau dt, which can we can put this equation here. So we will get the equation is equal to minus q by 2m and the qr squared by 2b. So we will get the delta mu, which means the magnetic moment change is equal to minus q squared r squared b by 4m. And in this case, we use the r, which is the r is equal to x squared plus y squared. And in reality, the electron will orbit the nuclear core in this r, and the r squared is equal to x squared plus y squared plus z squared. But in this model, we only orbit the electron is only orbital in this plane, which is x squared plus y squared. So for the average r, we can write here the average r would, in this case, sorry, I maybe write here. So the average r here would be 2 by 3 real r here. So sorry, it would be like this. So the average radius would be 2 by 3 r average here. So we can replace the r squared here as 3 by 2r. So the total number here is equal to minus qe squared times r squared average times b by 6m. So in the originally this is 4m, and because this is the factor of 3, so we will reach to the 6m. Okay, so this is the equations how to induce the magnetic moment by apply external magnetic field. So the change of the magnetic moment is minus some constant here, so some constant here times b, which means that the induced magnetic moment is proportional to b. So once the b increased, the induced magnetic moment also increased. So this is the principle of the how does diamagnetism coming from the electron that inside the atom. Okay, any questions? No? So in any case, we have found that the induced atomic moment proportional to the magnetic field and opposite it. Okay, this is the diamagnetism of the matter. No any question? Okay, then we will talk about the paramagnetism. So most experiments on the magnetic materials are performed at a constant pressure and involved in significant volume change. So we will measure its magnetic properties at ambient environment. So ambient environment means we have a constant pressure, which is 1 atmosphere, and their valence, because for the material at room temperature they don't have a significant valence changes. So in this case, we will study the paramagnetism at only 3 thermodynamic variables, which is magnetic field B, magnetization M, which is the sum of the dipole moments and the temperature T. And these methods of the statistical thermodynamics are appropriate since the alignment of the large number of atomic magnets is a statistical process. So for most of the students, they don't you never learn about something called the statistic thermodynamics. But for the magnetism, most theory is coming from the statistical thermodynamics. So maybe I will talk about a little bit from here. Of course, for the statistical thermodynamics, that would involve a lot of math equations. I will show you, but you don't need to remember that. You just need to know the final result. Okay, so the paramagnetic effects are produced in a crystal when some of its atoms have a net magnetic dipole moment. That is identical as what we say the uncompensated magnetic moment. Okay, uncompensated magnetic spin. Okay, so this net magnetic dipole moment associated with electron orbital angular momentums. They may come from the electron spin or orbital angular momentum, or both. So to understand the relationship between the magnetic moment and angular momentum, it is instructive to consider first case of the hydrogen atoms that they will give you a result for the more complex atom or ions. So the hydrogen model we already mentioned in the previous in the last class. Okay, so the basic ideas are the same for another system for the hydrogen. In quantum mechanics, we will describe the magnitude of the orbital angular momentum vector of an isolated hydrogen atom is L times L plus 1 h bar, root square of L times L plus 1 h bar. Okay, where the allowed value of the quantum number L are 0, 1, and 2. Okay, so I will give you some expression here. Okay, typically this is a nuclear core, and these are the orbitals here. In quantum, for the chemical department students, maybe you will know the atom from the atom core. There are different shells. The first shell is called K shell, the second is called L shell, and the third is called M shell, and so on. So KLM is the shell from inner to outer of the atom. And actually for the quantum mechanics, so the student comes from physical departments, you already learned that the first shell is called n equal 1, and the second shell is called n equal 2, and the third one is called n equal 3. So which means the K is the 1, and the L is the 2, and M is the 3. So that's the different notation in Department of Chemistry or Department of Physics, but they are all identicals. And in this case, the N is called the principal number, which correlates with the energy. Okay. So in another representations, in each orbital, for example, if we go to the n equal 3 orbital, they have different kinds of orbital shape, which is called the S, P, and the D. That would be familiar in some chemical class. And you have S orbital, P orbital, and the D orbital. And its shape would be like for S orbital, it would be look like a sphere. And for the P orbital, it would be look like this, and the D orbital would look like this one and this one. Okay. But in the quantum mechanics, the S orbital represents to the L equals 0, which means the orbital angular momentum is 0, and the P orbital is equal to L equal to 1. and d orbital represents to L equal 2. So SPD represents to the orbital quantum number or angular momentum here. The third one is called magnetic quantum number, which is the magnetic the spin angular momentums. Actually that would be called the eigenvalue of angular momentums. So the relation between the n, L, m is L is in between. L is the positive number that would be a little bit below n. So L equal to n minus 1 minus 2 until 0. And the m is the value that plus minus L plus minus L minus 1 plus minus L minus 2. So that would the m it will in between the plus L and the minus L. The plus or minus sign is because the spins have para or anti-para direction, so you will get the symbol of plus sign or minus sign. Okay, so in quantum mechanics we will write a notation like this, which contains n, L, m, and the n element is correlated with the energy, angular momentum, and magnetic quantum number. So in these pictures that I just connect or give you the relation between the NLM or KLM SPD that you learn in no matter in the general physics or general chemistry. Okay. Any questions? So let's return to the paramagnetism. Okay, so in quantum mechanics, the magnitude of orbital angular momentum is for the isolated hydrogen atom is root square L times L plus 1 h bar, and L is the quantum number L, which are 0, 1, 2, and so on. And then we know the z component of orbital angular momentum is mLh, which is in between the plus L and the minus L that I just talked about. So there are total 2L plus 1 value of mL. Okay, so magnetic dipole moment mu is proportional to the angular moment, and there will be a constant proportionality is I just write Q by 2me, or here we can write E by 2me. They are all identical, right? And E is the charge of the electron, and me is its mass. Okay, so we can write the absolute value of mu is equal to 2me eh bar times root square L plus 1. And here we can write it in the more short form, which is G mu B and root square L plus 1. And we also know that mu Z is equal to the G mu B mL. So this is the average magnetic moment of the for a certain ion, and this is the magnetic moment that project to the z-axis, which is G mu B mL. Okay, you will find the absolute value of mu is a little bit larger than the mu Z. That is the statistical result. I don't want to mention too much here, but for the high temperature, we will get the average magnetic moment. It looks like a G mu B root square L plus 1. But when we apply a strong magnetic field or at a low temperature, we will measure the mu Z values, and this value is equal to G mu B mL. So this form would be very valid when we about the ordering temperature, and this one may be used to no matter at a high temperature or low temperature, but at a high temperature you need to align all the magnetic moment to one direction and get correct value of the mu z. At low temperature, the magnetic moment will order it itself, so we will get a correct mu z from the experiments. Okay, so let's take break for the 10 minutes